So what I want to do here, I'm going to give you a few questions on the vector product using component form. What I want you to do is read the question, pause the video, have a crack at them, and then come back and check your answers with the working I'm going to present to you. So here you go. So I've got a couple here for you. First one, I want you to physically calculate the cross product if I give you two vectors. Second one is a hark back to the previous video using the angular formula for the cross product. And the third one, a little bit more of an application, is using it to calculate the area of a triangle where I give you the vertices. So pause the video and have a crack at these. So the first one, calculate A cross B if A is 4, -5, -6, and B is -1, -2, 3. Now again, I'm going to stick with the matrix form when I do this. As I've said previously, if you can remember that formula, good on you, and you can use it straight away. But what I'm going to do is represent it in my matrix. So I've got my I, my J, and my K, and I'm going to put my plus, minus, and plus above it. Then what I'm going to do is put my A vector, so 4, -5, -6, my B vector, -1, -2, and 3, and work my way from here. So look at the I component, so ignore the row in the column with I in it, and I've got -5, -6, -2, 3 in the I direction. I've then got minus, because remember the J column is minus, and again ignore the row in the column with the J in it. So I've got 4, 3, -1, and -6 there in the J direction. Then I've got plus, same idea with the K, ignore the row and column. What I end up getting is 4, -5, -1, and -2 in the K direction. So now I just do my wee calculations. So remember, diagonal here, take away diagonal here, products of the numbers. So -5 times 3, take away -6 times -2 in the I direction. So I'm going to be take away, same idea for the second one, 4 times 3, take away -1 times -6 in the J direction this time, then plus for the K direction, 4 times -2, take away -1 times -5 in the K direction. And now it's just calculating it out. So -5 times 3 is -15. -6 times -2, we can ignore the negatives. 6 2s are 12. So I've got -15 minus 12. So I've got -27 in the I direction. Then got my minus. If I look at the J, I've got 4 3s, which is 12. -1 times -6 is 6. 12 minus 6 is just 6. So it's then going to be -6J. I've then got 4 times -2 is -8. -1 times -5 is just 5. So I've got -8, take away 5, minus 13 in the K direction. So there you go. That there is A cross B, so that represents the vector normal to A and B at the point where the two vectors meet on the three-dimensional plane that is defined by them. Second one, I want to find the length of A cross B if A has a length of 4, B has a length of 5, and the angle between them is 45 degrees. Now this is a hark back to the formula from the previous slides. We will remember that the magnitude of A cross B is equal to the magnitude of A, magnitude of B, sine theta. Now from here, magnitude A, magnitude of B, they're the lengths, fairly self-explanatory, and theta is the angle between them, which in this case is 45. So the length, i.e. the magnitude of A cross B, that's going to be given by 4 times 5 times sine of 45. So magnitude of A cross B is given by 4 5s, which are 20. Sine 45 is 1 over root 2. So in this case, it's going to be 20 over root 2. As I've done previously, I don't like having an irrational denominator, so I'm going to rationalize it, multiply top and bottom by root 2. What I'll end up getting is 20 root 2 over 2, so 10 root 2. Now, if you don't have to rationalize it and you don't want to, that's fine. Don't worry about it. Like I say though, I just prefer doing it to get rid of a bit of a pet hate of mine. Last question, calculate the area of the triangle with vertices A, B and C given by these coordinates here. So what I'm going to do, first things first, sketch it. So right here is going to be my triangle where I've got my points A, my point B and my point C. Now remember, formula for the area of a triangle from previous is a half AB sine C. Now A and B are the length of the two sides, C is the angle between them. So what I'm actually going to do is I'm going to pick this here to be my angle C, which means that this here would be my A, and here would be what would be the equivalent of the line B. Now for this, A and B need to be scalars. So for this one, A would be the equivalent of the magnitude of AB, B would be the equivalent of the magnitude of AC. So I can rewrite the area as being a half times the magnitude of AB times the magnitude of AC times sine of C. Well, I'm going to call this angle here theta, because it's the angle between the two sides, which are now going to be the lengths of vectors representing AB and AC. Now what you'll notice is that this is the formula version for the cross product of these two vectors. So this here is the equivalent of doing AB cross AC. So I can rewrite the formula as being a half times the magnitude of AB cross AC. Because remember, we want the size of it. So we want to find this vector and then calculate the magnitude of that vector itself. So now what I've got to do, find my two vectors A and B, and A and C, and then put them in the cross product. So AB, we should know how to do this by now. So the position vector from A to B is equal to the point B minus the point A. Sorry, position vector for B, which is given by the point B, position vector for A, which is given by the point A. So in this case, what that's going to be given by is 5 minus 1, 2, take away 2, minus 1, 3. So in this case, it's going to be 3 minus 1 minus minus 1, which is 0. And I've then got 2 minus 3, which is minus 1 there. That's my AB. My vector AC, similar way, but except we're using position vector representing the point C this time. So it's going to be 2, 3, 4. Take away my 2, negative 1, 3 in this case. So this one is going to be giving me 0, 4, 1. So there you go, I've got my AB and I've got my AC. What I now have to do is calculate the AB cross AC. And again, I'm going to use the vector representation for it in terms of a matrix. I've got my I, I've got my J, and I've got my K. Again, I'll put my plus, my minus, and my plus on the top. AB in first, which is this one here. So 3, 0, minus 1. Then my AC, which is 0, 4, 1. And I just follow the same steps. So for the I, ignore the column and the row for I. And I'm left with 0, negative 1, 4, 1 for the I direction. For the J, it's then minus. And again, ignore the row and column for J. So it's 3, negative 1, 0, 1 in the J direction. And then for the K, same idea. This time it's going to be plus 3, 0, 0, 4 in the K direction. Oh, my line's got a wee bit of squish there. So what I now do, calculate each of these sets of components. So for this one, I've got 0 times 1, take away negative 1 times 4 in the I direction. I've then got take away 3 times 1, take away 0 times negative 1 in the J direction. And I've then got plus 3 times 4, take away 0 times 0 in the K direction. Calculate each of these out. What I'll end up getting is 0 minus minus 4, so I'll get 4i. Then I've got minus 3 times 1 here, because this will disappear to be 0, so minus 3j. I've then got 3 4s, which is 12. This is 0 plus 12. Okay, so that's me now got my vector for that. So now I know that the area is equal to a half times the magnitude of this here. So it's going to be a half times the square root of 4 squared plus a negative 3 squared plus 12 squared. So in this case, what that's going to be is if I calculate all of this out here, so square root of 4 squared plus negative 3 squared plus 12 squared, so that's 16 plus 9, so it's 25 plus 144, so it gives me 169. Square root of 169 is 13, so the area is 13 over 2 units squared. So there you go. What I've done is I've used this and applied this method and this technique to a shape made using vertices which I've represented then in terms of vectors and calculated it using the formula that we discussed previously as well as the component form calculation and brought it all together in one go. Many applications for this. We can use it for quite a lot of things and we'll see that throughout the entire unit and even throughout all of the matrices work if we go and look at that as well. Vectors are an important part of mathematics. Lots of applications beyond just a maths textbook. You need to know how to work with them and you need to be able to do this sort of calculation to ensure that you can cope with any task thrown at you involving them.